I'm using a board. I got video.
Well, good morning. Welcome to our science seminar. Today I'd like to introduce our introducer. I introduce Dr. Ball, longtime physics professor here at LeTourneau. And Dr. Ball is going to introduce our speakers for today.
All righty. Good morning. Welcome to the Science Seminar. You're in for a treat today. We have two engineering physics students that are presenting their work on chaos. And Aaron Conrad is a senior, and Luke is, where are you? There you are. They're both seniors. They're graduating this May. We don't want to let them go, but they're going to go on, I'm sure, to bigger and better things. And so they're going to be discussing some interesting things about chaos. And give them a warm welcome, please.
First, I want to say I know a lot of y'all just came from a test, so condolences, congratulations, and Godspeed to those of you who still have another one this afternoon. Better you than me. Okay, so I am going to be talking about chaos. First thing, though, a lot of people said that chaos is, oh, I know all about chaos. That's everyday life. Okay, fair enough. I'm going to call that hectic, though, for the sake of this. Then Dr. DeBoer let me know, it's chaos. Well, that's sin, which is also not what I mean. We're also not referring to the primordial chaos that may have existed before time began. Mathematical chaos, physical chaos, has a very particular definition that really has something to do with when we know what can happen, we just don't know what will happen. And to distinguish it, a lot of the science types of chaos, entropy, I know that one. Entropy is not quite the same. We talk about order versus chaos, but this is still not what we mean by chaos. We'll make it clearer. So typically, when people think of entropy, they start with a system with a lot of order, and then something happens, and thanks to thermodynamics, entropy gets into the system, and dadgummit, we lose the order that we thought we had. Still not exactly what we have in mind. So the easiest way, I think, to describe it, and the most formal definition that you'll probably find if you decide to search the literature, is an extreme sensitivity to initial conditions. Some of you may recognize this from carnival barkers. And I'm not going to call anybody to come on down, but this is a Plinko board. So the idea here is I'm going to take these washers and drop them in the same slot up here at the top and observe what bin they land in at the bottom. Every time, I'm going to put it right there. One more. So that's all sin. Not surprisingly, it looks like most of them sort of gravitated towards the center. We got some farther out on this bin out here, but it is also wider than the ones in the center. The two on the edges are the widest. So even though I dropped the washers in almost exactly the same spot every time, they never landed in the same spot twice in a row. Never the same bin. It's very, very sensitive to where exactly it was positioned to start with. And the idea is that it hits one of these pegs, and of course, it has a decision to make. It's either going to fall left or it's going to fall right. If more of its weight is on the left side, then it falls to the left, my left. If more of its weight is on the right side, it falls to the right, and then it does it again and again. And there's no particular reason, right, that it should fall to the left or to the right, other than the initial conditions. And it makes me think of the joke, if a rooster were to lay an egg on top of a pyramid where each side is facing cardinal directions, where does the egg fall?
It doesn't. Roosters don't lay eggs.
That's right. But in real life, if a rooster were to, no, if there were to be an egg right there, it would have to fall somewhere. It's not just going to sit there. You can try to balance a pencil on its tip, but you won't. So it's very, very sensitive to initial conditions. And what's happening is what we call a symmetry breaking, left versus right. There's no particular reason you should pick one. So there's a classic example of symmetry breaking in what we'll call nonlinear dynamics. And we'll come to why that is here in just a moment. That is the spinning hoop. So we've got a frictionless hoop, we'll say, with regular gravity, and a bead that's free to slide along the hoop at whatever, without friction. So initially it'll just sit here at the bottom. If we spin the hoop, then eventually the bead is going to experience a centrifugal force, and it's going to push it towards the outside. Centrifugal force doesn't exist. Yeah, the bead experiences centrifugal force. There's math. So, at the beginning, it's going to be spinning really slowly, and the bead will just stay at the bottom. That makes sense? That's its equilibrium point. But as we get it spinning faster and faster, it's going to have to pick a side, and it's going to get flung to the edges. So, I came up with, I really wanted to make one of these, because I've read about them and I've never actually seen one. So what I've got is a little frame where this hoop is suspended, and this nut is a common ground, so that each sides are electrically insulated from each other. When it goes over here, that light will come on. When it goes over here, the yellow light will come on. So that way, even when it's spinning, we'll know which direction it went. Otherwise, it's really hard to tell on a perfectly symmetric hoop which way the nut slides. So I was coming up with this little gizmo. So again, the idea here is that we know what can happen, we just don't know what will happen. Yellow side. See the ring? Yellow side again.
Likes the yellow side.
He likes the yellow side. It's also not a perfect design, I'll admit.
Would it have anything to do with the wire?
Oh, okay.
Alright. I'll do it one more time. Thank you for clapping. I was really proud of this. I've never actually seen one. I've read about it a lot. He actually clapped. Somebody here clapped. I appreciate it. It's not as good. Okay. Anyway. So, we've made it this far without actually doing any math or looking at any graphs. But this is science, by gum, so let's make a graph. So here we've got, on the vertical axis, the angular displacement from the bead just hanging down here at the bottom. Right? We've got, it was the phi represented on the previous picture. And the horizontal axis is how fast the hoop is spinning. So, like we said, up to a certain speed, it's just going to stay at the bottom. And so, it'll be at zero displacement until we reach somewhere where the centrifugal force takes over and it can't sit at the bottom anymore. And this will split it off into two possibilities. Left side, right side, yellow side, bright white side. Bifurcates, what we call this. This is a bifurcation diagram. And eventually it'll reach a stability point so that that's its new equilibrium. No matter how much faster you go, that's where it'll stay. And of course that's horizontal. That's going to be pi, negative pi over 2. So this is important. The reason that I want to focus on this is a bifurcation diagram. This comes up a lot in chaos. Okay. The thing to note is that if you put in some given omega after the bifurcation, you can't actually predict what phi will be. That is, for some given speed, we don't know exactly where the nut will rest. It's extremely sensitive to the initial conditions. And that's the criteria that we wanted. That's chaos, baby. All right. Another good example is a single arm pendulum. In this case, you're literally going to get a single arm, because I don't have a demo of this one. So, it has two stable modes. Either it'll just hang straight down and not move. It'll stay just like that. Or, conceivably, it could stand upright. Right? If it's just a pendulum with no friction, it could stand perfectly upright. But again, this is balancing a pencil on its tip. Good luck. So, I'm going to draw a little bit here. Let's make another graph. I can't raise this. So, here. The two things that I'm going to be curious about here is its angular displacement from vertical, as it swings like this. So we'll call that theta. And then the actual speed at which it's swinging. Because once it comes up and turns around, its speed has to be 0 for just a moment. So we'll have theta and theta dot, which nobody will be able to see. Let's see if it's more visual. Ah, it is. Love it. Theta and theta dot. So, like we said before, if it hangs straight down and it's not moving, it's not going to move. So we can just put just a spot right there. Now, if it had some, right-hand rule, if it had some initial positive velocity and was swinging upward, it would continue until theta dot reached 0. So, let's make a note here. It'll be at some angle, and eventually its angular velocity will come to 0, and it'll turn around. Theta goes closer to 0, so it's going to be moving this way, because theta is going to swing back. Oh, y'all can't see. Sorry. So it's going to be moving back towards 0. Let's see. Sorry. And eventually, it'll be at maximum speed. It'll have the most momentum whenever it's right here. And then it'll start slowing down again, because gravity's going to kick in. Now we're saying there's no friction, so we don't have to think about that too much. So we'll have another point here, and it does move in this direction. Now it's actually going to get to that point, and then swing back, and forth, and back. So whatever our initial conditions were, it's going to cycle through about like this. And it's always going to go in this direction, too. It's always going to go counterclockwise. Even if we were really close, and it was just barely swinging, we'd still have one of these. And even if it was going really fast, we'd still have something shaped about like so. It's always going to spin in this direction. Okay? That's one way they can oscillate. Or, it can swing all the way up over, and then slow down, so it'll be at its slowest, what that is, straight up, and then it'll start speeding up again, and come back down, and loop around like so. We'll make that a different color. So let's see. When theta is 0, it'll be going its fastest. And then as theta increases, let's actually give it a name. This is pi, right? We've got the 0 down here at the bottom, so we'll have pi up here at the top. Right there. Pi. Negative pi. Signs don't matter. It's periodic. So it'll be slowest right at the top. So theta dot's going to be its lowest value right about here. So we've got our first eyebrow. We'll have more. You might be able to see where this is going. We can get really close to oscillations that look more and more like a so-called steady state. But there is a distinction, of course, between it coming out like this and swinging back versus coming out like this and making it all the way up over and then swinging over to the other side. Where does that distinction lie? On the floor. Because there's no way that theta, they can be straight up and not move and then move. There's no other forces other than gravity, which is conservative, and there's no friction here. So somehow this is off limits and this is off limits. And as a consequence, there will be some regime that separates these two stable modes of oscillation. This is the eye of chaos. Conveniently called the separators. I love the sound of separators. Okay. Oh yeah, equation of motion. This makes sense that it would be a nonlinear system. We've got a sign in there, so we can put in some particular theta dot, but that doesn't actually tell us what our theta will be, and vice versa. We've got to pick both of them. These are our initial conditions, and then we can have an idea what we're going to have of how our system will behave. Wonderful. So this one's a little bit easier to visualize. Hopefully everybody can see it. I really, really wanted to draw it though. Okay. That's a single over pendulum. Now if we did introduce friction, that spot in the dead center is actually conceivable. Eventually it'll stop swinging and it'll just sit there. And so we end up cutting all the possible states into sections. These are called basins of attraction. Because if you start in the shaded area anywhere, you're going to end up right there in the center. All roads lead to naught. All right, now let's actually do some math. Early on in differential equations, you start working with the logistic model, which has to do with how populations evolve. It was a really good first guess. We've gotten better at it since then. But typically you'll do it in continuous time. This is an iterative approach we're talking about here, called the logistic map. A guy named Verhulst came up with it, and we get this difference equation. So if you were to expand this, you get mu times x minus mu times x squared. So the graph sort of makes sense. You've got a parabola pointing down and some positive linear graph. And with a little intuition, you'll see that it will bounce back and forth between the two, more or less. In this example, just to show that I'm not pulling your leg, if you actually plug in our parameter mu is equal to 2, and you start with x in equal to 0.2, then after one iteration, you've got 3.2. You can distribute it, you figure it out. So what this represents, we start with x at 0.2, and it goes up to, excuse me, I said 3.2, 0.32, pardon me, 0.32 on our chart. And so going up one represents an iteration, and then the horizontal movement is just so that we can actually see the behavior. In this case, conveniently, it converges to a finite value. Right there, it sort of bounces in and then finds the corners, and it's stable there. That's a stable population. That's not how it always works. Sometimes it can sort of oscillate between certain values, and this is not uncommon. We can imagine this happening, especially once you introduce predator-prey and all this fun stuff. But it has this periodic dynamic of sorts, where you can actually pick out how many iterations it'll take before you come back to a certain value that you obtained earlier on. And on the right, you can see sort of a population value versus iteration number. In continuous time, it would look a little different, it would look a little smoother, but it would still orbit. This is a single period. Sometimes it takes more than one actual cycling through before you come back to where you started. In this case, there's 2 periods. And you can see the main loop coming in and having a smaller loop and then going back to the outer loop. In chaos, we call this multi-periodicity. We've got multiple periods. It's also really convenient that we pick up where we started eventually, that it actually repeats. That doesn't always happen. It's extremely sensitive to initial conditions, and so these particular graphs are well selected to graduate to the next thing called quasi-periodicity, which is where anybody's guess goes. And the longer you iterate it, the crazier it gets. On the right is, again, a population value versus iteration, or how it would evolve over time if we were working in continuous time instead of iterative steps. This quasi-periodicity comes up a lot, and it makes it really hard to guess where a system is going to go next. Again, we can form bifurcation diagrams. I mentioned those are really important. This reinforces the nonlinearity of the system. And notice, if you zoom in, if you were to zoom in here, you get almost exactly the same diagram. If you were to zoom in then again, right there, you get almost exactly the same diagram. We've got that extreme sensitivity to initial conditions. And even better, we know what can happen. But if you plug in some value for mu, we don't know what will happen. So we've got perfect candidate for chaos here. All right. So this complexity, whenever you zoom in more and increase the resolution, and you can still zoom in more and increase the resolution, and still zoom in more and increase the resolution, and never really get anywhere as far as understanding what's going on what to expect next, I should say. This leads to fractals. Fractals, sort of how rough a graph is. A lot of people think it has to do with the repeating pattern. Sometimes. In this case, it's conveniently repeating. So here, if we were to imagine the previous system in continuous time, it would loop through and have these multiple periods. One can imagine a track, almost, that the system would follow as it repeated these different periods. Sort of, you know, like a weird-looking Funyun. And it was just constrained to run along this Funyun over and over with however many cycles. A weird-looking Funyun. And we can fold these to be all kinds of weird shapes. And because it's constrained to stay on this, and if it starts off of it, it'll come back to it, we call these shapes attractors. And so if we have a three-dimensional system, we have a four-dimensional attractor. We had a one-dimensional system before, so we could have formulated a two-dimensional attractor. Again, we've got multiperiodicity. In this case, actually arriving from this folding of our weird-looking Funyun into different tracks that it can follow. The arrows and lines represented here we call limit cycles, because this does represent a closed period. It may be multi-periodic, but eventually it'll come back to where it started. Quasi-periodicity won't do that, and it'll be all over the place. Eventually it'll cover the whole track, and in some cases it'll never repeat itself, and it'll form, we call that spanning the space. In linear algebra, you'll have to do something like that too. Okay, so the system is constrained to move along this. Notice that there's an extra fold on this one. This is trying to help visualize what comes next, because the next part is the fun part. Okay. One really good system, what we want to look for, so we mentioned nonlinearity, got a good candidate for that. We mentioned mixing. Excuse me. We haven't mentioned mixing. I'm about to introduce you to mixing. We want to have as many dimensions in our system as we can to get some really robust behavior. And it's all that much more fun if the different dimensions sort of overlap with each other. So we talked about a single pendulum before. This is a double pendulum. Uh-oh. I've lost my place. Come on now. Aw, stole my thunder. Double pendulum. This thing has a mind of its own. Just kind of let it go for a second. So, the equations of motion are really complicated. Solving these is a bear for anybody. So the nonlinearity is obvious because we've got sines and cosines, and those are definitely not linear. We've got mixing even. We can characterize our system if x is the pivot. We'll have one arm here, another arm connecting that. So from horizontal, we'll have what we'll call theta 1 and a theta 2. And just as for the, some of you can't see it, too bad. Just as for the single arm pendulum we looked at the angle and the angular velocity, for the double arm pendulum we're going to look at the angles and their angular velocities. In the first case, theta was periodic, meaning that once you went all the way around you ended up back where you started, which makes sense because you went in full circle. And so was theta dot, which is significant because that means that sort of no matter where the clicker went, where the pendulum went, we eventually knew that it would end up back in a certain space, and that's how we were able to formulate the way we were. In this case, though, we've got a system with 2 degrees of freedom and 2 associated degrees of freedom, and they're all periodic. So if before we could have wrapped it around, say, a sphere, where you go off one side, you come back in on the other, you go around the other way, you come back in. Now we've got 4 degrees of freedom. So we've got a 4-dimensional system. And it'd be shaped like a torus. We can't visualize a 4-dimensional system. It's as much fun as it sounds. It hurts as bad as it sounds. But I did put a torus up here just to have an idea. So before, I said that it spanned the space. And the idea is that the combinations of theta, theta dot, theta 1 and 2 dot, that this will take over time is going to be constrained to wander along the surface of this four-dimensional torus. This is topology. This is the fun stuff. Okay. And if for any initial conditions, it will never come back to where it started. Not exactly. It's too sensitive. That's really, that's chaotic. And so eventually it'll cover the entire torus. If it could go on for all time without any friction, it would cover the entire four-dimensional torus. So the next part, this is my favorite slide. It's a two-dimensional slice of a three-dimensional slice of a four-dimensional object. Two slices, actually. I ate an onion like that once. I love it. Now the reason that it takes this shape is because it will eventually take up all the space that it has, but it doesn't have to go in any particular order that we can impose on it. So on the right and left, you'll see we've got E1 and E2 and momentums and all this stuff. That's cool. That controls what order it goes through the different states. We know it's going to go through all of them. And the order in which it does that gives us the weird shapes in 3D and the weird slices in 2D. Okay. The guy who first came up with the attractors was named Lorentz. He was actually a meteorologist, not a physicist, and he was trying to predict the weather. And he was trying to factor in as many things as, you know, wind speed and barometric pressure and stuff. So I'm gonna show sort of the first inkling into chaos that we ever actually had. Oh yes, thank you. The emphasis here is that the green dot and the blue dot represent particular states of the atmosphere at a certain time, and he wanted to predict what would happen next. And we're getting them very, very close together, and we'll see how it would evolve over time, according to the equations he came up with. So they started really close together, and they're following the same pattern more or less, but they get farther and farther apart. And they missed each other. They come back together. So, I'm going to skip to a part of this wonderful video where he actually speeds it up and traces the tail of these two states, trajectories. And since it would eventually cover this entire surface, we can let it evolve over time long enough and get an idea of what this attractor that Lorentz called strange, these are strange attractors, would actually be shaped like. For those of you that have taken Calculus 3 or differential equations, there's an underlying vector field that's pushing these states in the, thank you. It's pushing these states into the shapes that they're given. Sort of, as the water shaped the Grand Canyon, so does this vector field shape our attractor. That was the first chaos. And that, ladies and gentlemen, is the butterfly effect. Forget all that elephant sneezes and whatever in Brazil. No, it was the butterfly that he saw whenever he graphed this. Okay. I think the next slide. And now, Luke has actually built himself a very chaotic system for a summer research project, and he presented on this in the fall at a physics conference. So he's going to let us know a little bit more about how that went. I'm going to turn the lights back up.
Give you a tidbit anyway. So, after Lorentz discovered his butterfly attractor, a lot of people got really interested in chaos and were trying to find different ways and different systems that would exhibit chaos. And you've seen several examples here, but all of these examples have in common that they are physical systems. This one, all it requires in an ideal system is that you give it a little push. Leon Shua, however, had the brilliant thought that why don't we find an electronic circuit that could exhibit chaos? Let's try to do that. But that's kind of very challenging, really, because so many things in circuits are linear. Resistors, linear, capacitors, all the others, they exhibit fairly linear behavior. So, eventually, he came up with this, which is a negative nonlinear resistor called Shua's diode. So as the current increases, the voltage doesn't go up on a straight line like most resistors. And that's because of these op-amps. These op-amps amplify things and just do weird, funky things. And he created the rest of the circuit using a capacitor here, another capacitor, and this approximates an ideal inductor. So there's a very, very simple circuit here to exhibit chaos. And it kind of follows a pattern. These things are also very simple, but exhibit weird behavior. Now, you'll remember the bifurcation diagram. I put all of the equations into MATLAB and generated my own bifurcation diagrams. And based on the parameters, you get this. So here you have very chaotic behavior. Here you have, again, pretty chaotic behavior. But in the middle, you get this kind of ordered sense. It's a little bit. You still have this bounding. You still have some funky area filling stuff. So you still have some chaos, but it's a little bit ordered. Now, if we zoom in on 29, that's this section right here, we get this. And you can see more the transition between chaos, order, chaos. But here, there's more. Order, chaos. So let's zoom in a little more. Right, real close here. See, we're down to going just, what, 1/100th across that parameter. And you see more transitions. There you go, more transition. Order, chaos, order, chaos, order, chaos, order, chaos. It just doesn't stop. And so I got thinking, well, how long do I have to go before this smooths out and I can see something nice and continuous and pretty that I can put up on a poster and say, I got this. So I zoomed way in. Now that is a separation of 10 to the minus 11, I believe. And, well, it's pretty much the same thing, really. You just get order, chaos, it never stops. What does that remind you of? Fractals. Someone said it. Fractal behavior. That's right. So it's very likely that this circuit, at least in this particular piece of the parameter, exhibits fractal behavior. You could zoom in as much as you want, and it'll never even out. It'll still transition into chaos and order and chaos. And if you look here, you can see, this is the physical circuit. I made it on the oscilloscope here. You can see an attractor made. And see it's all moving and it's kind of shifting. It's because it's very, very sensitive. So even little vibrations in the room, even the tiny oscillations from the power supply and the oscilloscope are changing things, and it's making it shift into different regimes of order and chaos. And I also simulated the attractor. So here you have a very, very ordered attractor. It's almost exactly on the limit cycle. Very, very little deviation. Now, if you'll notice, that's a beta of 29.548. What about 29.549? Tiny little change, but you get chaos. A substantial amount of chaos relative to the first attractor. Very small change, big change in chaos. What if we change it from 29.549 to 29.5491? Again, this very, very small change exhibiting a very big change in chaos, fractal behavior, and a very pretty graph. So, what's it actually look like? This I changed. I did not do this using the resistors I have here, but you'll see this transition from a bifurcation. You'll see it bifurcate and go from this single scroll and stretch out into a double scroll, and then back again. And different regimes of order and chaos. So there, it's getting, there you see some more order, and it'll snap into another, there, order, chaos, order, and there it disappears. And then, back again. And just dialing it backwards, the other way, see these transitions into order and chaos that are very unpredictable. They don't follow any consistent pattern. And it's much easier to see the order on a screen with a frame rate because they transition so fast that sometimes, as I was filming it, it didn't look nearly that ordered, but the frame rate caught just the right moment to catch order. And that was basically my summer research, was investigating this funky, weird, cool, bizarre behavior.
There are lots of other, thank you. Luke, that's really cool. I'm glad you're showing us that. There are a lot of other attractors also, and they have some weird shapes and some weird names. The one that Luke showed us was a double scroll. The one before was a butterfly attractor. Those are called double lobes. They make them with however many scrolls you want. They're like loaded up like cup holders. All right. Time for some conclusions. So the first thing is that we may have a really good idea of how the equations evolve, and we can characterize it in terms of time. But even what's called a deterministic system is not so exact as one might think, because we don't have absolute knowledge, we don't have absolute precision. So a lot of people like to imagine the God as a watchmaker idea, where or that we could play God as a watchmaker, where if we had perfect control and knowledge of a system with some given tolerance, that we could figure out exactly what would happen. But we can't have knowledge, we can't control it that precisely. In fact, at the point where you say you would, then you get quantum mechanics takes over, and that's a whole other barrel of monkeys. Stability, we like to think, as in the first example with the Verhulst model, means that we converge to some constant value and we can control what that value is. But sometimes we can just settle for recognizing that things come in seasons and come in cycles, and there's a time for it to go high and another time for it to go low. And this is how life works, and sometimes it's a little chaotic. Also, chaos has the coolest graphs in math. Yeah, that's the way it is. I want to emphasize also actually about this graph. This is nonlinear, but it is actually not chaotic. Nonlinearity is required for chaos, but not sufficient. So check out just Google some strange attractors. They get some really funky shapes. A lot of people like setting up their background. Like this one. Yeah, there's all kind of cool stuff. All right, and now Luke and I would love to answer any questions that you can have, anything you might want to holes in. So appreciate it.
All right.
Okay, so I know that the meteorologist was the one who kind of came up with this idea of these attractors. And I know that to CubeSat team is trying to predict the weather. Are y'all working with the CubeSat team at all?
Nope.
Okay, all right.
Good question. Go ahead.
What's the end game of this research? Like,
Chaos?
all researching chaos, other than the fact that it produces cool graphs and it's fun to see patterns or lack thereof in the universe, like, how can this help daily society?
Good question. First, we can predict the weather. If we got good enough, possibly we can predict the weather. The first thing that comes to mind, and Dr. Barnett could go, if you ask him about it, he would go on and on, about the Bernoulli equation. And some of the effects that you get with boundary layer separation, turbulent versus laminar flow. Turbulence is a molecular level actual chaotic system where we know what can happen. We have an equation that can describe it, but it almost doesn't do any good, so that we have to generalize it. And then it goes from being physics to engineering.
Okay. Can I jump in on that just for a second?
Please do.
Yeah, a lot of systems that involve human behavior are intrinsically chaotic. A good example of a system that has a lot of chaotic characteristics would be the stock market. And if you want to make a lot of money knowing quantitative information, and you can make any useful predictions about regions of stability within the extremely high dimensional parameter space of the stock market's behavior, you will be of great interest to a lot of employers. There's kind of this cliche back in the 90s of people with physics degrees going off to Wall Street and making lots of money because they could do even relatively simple nonlinear predictive behavior using computational physical models.
Now we call it econophysics.
Yeah. It's a thing.
Cool, so now everybody understands chaos. Go ahead.
Question specifically for Luke. Why did the graph in the video just go?
Well, because let's point to this. You can think of it as modes, right? These different attractors and different regions of stability have different modes. Well, if you go too far past the parameter, then you get into a stable mode where it's just oscillating evenly, continuously in a sine wave, or a stable mode where it's just flat. Nothing's happening. And so what happened when it just went out was that I adjusted the voltage past where that parameter would collapse the attractor. And it was completely stable. And so then when I brought it back in, it brought it back into a regime where those parameters exhibited chaotic behavior, and it popped backward.
So that would be in line with the chaos, all depending on the initial conditions.
The chaos depends a lot on the parameters in the equations. Can we bring up the Lorentz equation?
That's on a hidden slide.
It's a ways back.
Yeah.
Here. So here you have parameters beta, rho, and sigma. And depending on what those parameters are, you'll get different types of attractors and different things that can happen. Now the initial conditions, you don't know exactly where it would be on the attractor, right? The parameters determine what the attractor looks like and how far out you can go. But the initial conditions just kind of, you don't know where it'll exactly be. The bead, you don't know where the bead will be, but the attractor is determined by those constants. Yeah.
These equations work for every attractor.
Every attractor has a different set of equations. So this one specifically models the Lorentz attractor.
So given it's chaotic, is Lorentz a stable genius?
I don't think any genius is considered stable.
No.
I'm sorry. There's more questions, go ahead.
Would this chaotic behavior be synonymous with, say, electrons and the fact that we can't know exactly where it is at one point, but we know the general area of it?
No. And it's really sad. Actually, the breakdown, quantum mechanics did away with determinism in a way that people never thought it would. And then even on these larger scales where we can make equations like for these systems, we still lose that determinism, but it's not the same thing as quantum uncertainty. There is quantum chaos, but it takes on a different meaning. And people actually come up with a new word for it. Chaology. Yeah. That's a really good question.
In the beginning, you said that chaos was not the same as disorder. But Luke was using the term, I think, interchangeably.
Somewhat.
So
That would be a fault terminology on my part.
and throw in randomness. How does chaos and randomness and order and disorder, how do those relate?
Okay. Random would be more like in the quantum mechanics stuff. This is science. Words mean things. So order and chaos are not antonyms in mathematical chaos and in physical chaos. The places where Luke was talking about having an ordered regime, I can go back to the bifurcation diagram. In these, for the parameters that he was given, the bifurcation diagram was relatively nonlinear. So in the places where it looks like a dust storm, it could, for any given value of beta, it's represented by B, it could be anything you would draw a vertical line through. Places that he was interested in have fewer options, basically. And so call it more well ordered. It's very clearly nonlinear, and it's the result of a chaotic system. Randomness means we actually don't know what can happen a lot of the time, right? So that's why I really like the idea that we know what can happen with chaos. We just don't know what will happen. Now, with quantum mechanics, you describe particles as waves, and you can say the wave is everywhere, so it's got to pop up somewhere. So sure, we know what can happen, but people can't even agree over what those waves actually represent if it's a probability density function. So randomness is being integrated into chaos for things like nuclear physics, as a matter of fact. There's something called random matrix theory that people are using to simulate the strong force that goes on inside of a nucleus. So that might be a chaotic system. We can simulate it with our pseudo-random computer-generated matrices and plug it into algorithms that replicate it, but of course it's still a simulation. Does that feel satisfactory?
Yeah, that's helpful.
Okay. Thank you. That's I appreciate the semantics. Words mean that.
Well, I just want to say on behalf of Dr. Hamilton and myself that we're very, very proud of these guys. These guys have done an excellent job. And I don't know, anything you want to say, Dr. Hamilton?
Yeah, I thought that was a great talk. I really enjoyed hearing it.
Thanks. I'm good at talking.
But you are an entertaining and engaging speaker. I hope that someday you get to be a teacher.
Yeah, these guys
You
need
could
to
be
get
the
their
next Bill
PhDs.
Nye.
We'll come back in here.
Conrad.
All righty. Listen, if you want to learn more about what these guys have been working on, come to lunch with us here afterwards. We're going to be down in the Joyce Room. I want to announce that next week we've got another special science seminar coming up. It seems to be getting better and better. We got John Dejay who's going to be talking about radioactive waste on next Thursday. So thanks for coming out for that. And let's give our speakers one more round.